Hi, I'm Haibin. I'm from Biden's machine learning system team. So today I'm going to share some of the experience we have for scaling large language model training over a really large cluster. It'd be a huge cluster. It could be like more than 10K GPUs, right? So I hope you can gain some insights about the challenges and the method we have in terms of how to train these kind of models with high efficiency and high stability. So let's get started. So here's some background about the applications we're trying to build. So at ByteDance, we released a AI assistant chatbot last year. So it is a chatbot. You can use it as a tool. So you can, ask it to help debug some of the code pieces or build some code pipelines. So you can also, ask the chatbot to create some content for you. You can, ask it to draw some images based on the prompt you have, and you can also, just casually chat with this chatbot about some problems you have in a day or ask for suggestions or advices. So behind these chatbot, so there's the model that's doing all the work. It is the large language model. And to train this kind of large language model with very high quality, basically is the key point that is behind these applications. So how do we achieve this kind of high quality language models? So uh, look at these steps. So there are basically 4 steps to train these kind of high quality models, right? So we start with the pre-training phase where, we have to collect all the data from the internet. So we crawl the data from the internet and let the model basically compress all the knowledge from the internet that is general purpose. And then we can prepare some human labeled data that is designed specifically for a task that is called supervised fine tuning. So basically, you can adjust the model and instruct it to follow your intent for specific tasks. And later on, you can do reinforcement learning from human feedback, where basically the language model is uh, adjusted based on the human preferences and adjust its output so that the human like it better. And finally, you can put model online for serving. And this is the way you train all these models. And the most time consuming and most uncertain part is the pre-training part because each take would consume a lot of resources and it takes very long time. So each uh, take could take a few months actually. So uh, if you want to calculate the computation resources required for this step, it basically scales linearly with the dataset size and the parameter size. But for language model, it's very important that you get a really large data sets. The larger you have, the more quality you get is better. And also the number of parameters is very important because a larger model means that it has more capacity to store, remember, and learn all this knowledge. So that means, oh, wow, we got a lot of computation resources to really train these models. And as a reference, if you train a GPT-3 with 300 billion tokens, it could take one DGX A100 node for a decade, right? So that's why we really need to build a really large cluster to train this model and improve the efficiency. So in the past, I've been building these kind of distributed training frameworks and trying to optimize them. And here I'm really excited about these kind of challenges we have. And there are mainly two. One is training efficiency at scale because each training takes a few months. Because at the efficiency side, the language model training is doing synchronous updates, so that's defined by the algorithm. So it's not embarrassing in parallel. On the other hand, because the model is so large, so you have to shard the model across different nodes. So the communication between different nodes and even within a node could take a large fraction of the time. So it's very important to optimize this kind of communication overhead. So that's the day-to-day work as an ML sys or engineer. And on the other hand, if you have a cluster that is more than 10K GPUs, and even just with 3K or 4K, you will hit stability problems with the cluster. So there are faulty GPUs that's happening from time to time, and as the number of nodes increases, it happens more often. So basically, if you have a training job that lasts 4 months, then the failure and stragglers are the norm. So you need to handle them automatically. So now I'm gonna uh, share a bit more about how we handle these kind of challenges. And the system we built is called MegaScale. It's also being open sourced in this repository here. Basically, it's a rewritten version, and it's much cleaner, and we're still working on it. So on the efficiency side, so there are a few things. So first of all, we need to build profiling tools to understand the performance characteristics. So with this tool, you can gain some insights. And then we optimize the very important part, which is the communication. We enhance the communication overlap techniques in the 3D parallelism that is typically used for like billion or trillion parameter model training in the industry. Okay, so let's look at some more details about our solution. So first of all, the profiling infrastructure, right? So with this large model, there are a lot of nodes participating in the cluster. And with the 3D topology, you can visualize what's happening in terms of the relationship of the nodes as well as the networking traffic. So as you can see, there are traffics within a node. There are also traffics across nodes. So there are peer-to-peer communications. For instance, the PPCom, which is the yellow line here, as well as the green ones, which is happening inside the node. So with tools like Torch Profiler, we can gain insights from the kernel level profiling on a single device. So basically, it tells you how much time is spent on each kernel within a node. But that's not very sufficient for analyze the training job from an end-to-end perspective, right? So we also built a distributed profiling tool, which is a tool that helps you connect different events across GPUs, across nodes together, so you can see how the data is flowing from one node to another, and you can analyze the dependency as well as the whole time span, how the where the time has gone in a single training job. So with this tool in place, now we have some insights about the dependency within the node and across nodes, and optimize the communication upon it. So let's look at the case for the intranode communication. So this is mainly referring to as the tensor parallelism or sequence parallelism in the typical language model training. So basically, it splits the one layer of the model training inside a node across different GPUs. So on the left, you can see a figure that is one variant of the transformer architecture. So each box is a computation node. And so you have some layer norms, some matrix multiplication, and all, right? So what I want you to focus is there are two matrix multiplications here called column parallel linear with altogether, another called row parallel linear with radial scatter. So basically, we have this sequential dependency between a matrix multiplication and a collective. It could be a altogether node or a radial scatter. So for this kind of dependency, usually you have to do it one by one. So when you do communication, you cannot do computation. But you can actually optimize it further. So what we did is to break it up into small chunks. So here, the matrix multiplication done in 8 chunks. So for each chunk, when you do the matrix multiplication, after it's done, you can start doing the communication for this chunk. So this is a more fine-grained version. And so this way you can pipeline some of the communication and hide the overhead of that. right? So we are also working on even finer grained version where we do it at even smaller tiles. But you kind of get an idea of what kind of techniques we can do inside a node for the transformer architecture. Okay, so then we can look at the internode communication. So this is usually the data parallelism that is taking a lot of time. And here for data parallelism, typically what you do is the typical forward and backward pass for the model training. And the communication is mainly about synchronize the gradients as well as gathering or synchronizing the parameters. And so if you look at this pattern carefully, so for the gradient part is followed by the backward pass. So you can actually do it in chunks or layers as well. So if you do the backward pass for one layer and start doing the gradient sync immediately after it, so you can actually start the next layer's computation backward. And so the backward computation is overlapped with the gradient synchronization. And you can do it similarly for the gather. So that closes the for loop. So you can actually overlap the majority of the gradient synchronization or gather parameter synchronization for the data parallelism. Okay, cool. So after we look at the techniques for internode and intranode communication, here are some results for the training performance, the overall training. So we are comparing Megatron that was released earlier last year. So uh, we test with different number of GPUs. We also measure the model training performance with the metric model flop utilization. So it has a upper bound 100%, which means utilizing the full flops of the GPUs. So if you look at the MegaScale results, so it is actually pretty good with the optimization. So it's about 1.3x speed up over the baseline. And it is even more surprising that with these optimizations in place, you can actually train GPT-3 over 300 billion tokens in less than 2 days. So you can really iterate a lot faster. Cool. So now we talked about our efforts for the efficiency part. Now let's talk about the stability issues in the cluster. So we hit this problem once we get more than 3K or 4K GPUs in a single training job, and it becomes really severe for more than 10K. And the very important thing we do is first to develop a robust training framework, which handles all the GPU faults automatically with this framework. And of course, we need to handle the checkpointing as well. So we use checkpoints to save and load the states of the training progress. And we need to make it really fast by optimizing the serializations and data movement from memory, disk, and remote storage. And finally, we develop some tools and we'll share some case study on the kind of struggle issues we got and how we solve them in the cluster. So let's look at the robust training framework. We have the Kubernetes for scheduling in ByteDance, and usually you have a single training job. When we started, the Kubernetes would ask for resources. So here, each executor on the graph is a GPU node, and if you run the training job, usually the executor would provide heartbeats to the driver so that the driver knows everything is working correctly and is working fine. Now, say that the training job hits some errors or some failures. It could be a GPU hang or some ECC errors indicating that the GPU is not correctly working. Then there will be the driver checking all the executors, check the status of the each GPU, and potentially run down some tests. It could be some lightweight test at the beginning, for instance, just running some small computation test, as well as some memory test, as well as some heavier ones like computation, like nickel test across nodes. So with that, usually you would automatically handle maybe 90% of the faults in the cluster. And for the driver, it basically knows the GPUs that need to be blocked, and it will evict all these faulty nodes and replace them with a new one so that the uh, the training job can resume from the last checkpoint and continue from that. And sometimes you can also intervene with a user API to, investigate and check the step trees of all the different GPUs to figure out what's happening and do some human analysis if the automatically training robust training framework cannot handle it. Okay, so here is one graph that represents one training job over a few months. So it is taking a lot of resumes. So each color here means one training run, one training period. And you can see that it stopped a lot of times, but it managed to converge all the way through, and it's not, divergent or anything. So with the robust training work, we can train really large models over a long period of time. And there are interesting things we found in the cluster. For instance, there are computational stragglers that is found by our distributed profiling tool. And basically what happens is the training job is slower from the beginning, and it keeps at a very low throughput. And if we look at the cluster profiling, we can find that there are certain GPUs always performing the matrix multiplication slower than the others, and then we can kick them out. On the other hand, there are also mysterious things like decreasing throughput during the training. So initially, maybe the training is working correctly, it's working fine at a very high throughput, but over the time, it drops. So here, each color represents a training period. And so you can see that to analyze this problem, we stop the training a few times, but for each training, if it runs long enough, it starts to drop from the throughput aspect. So from that, we actually found some issues in the memory management module and found some memory leaks. So after fixing those memory leaks on the CPU, then the training throughput becomes normal again. So this is one interesting problem we found, and here's how we fixed it. All right, so we're also continue working on a lot of new things. So the issues we talked about is mainly targeting the dense model, but there are more new model architecture coming out. There are the mixture expert models, which is a lot more sparse, and it requires different communication and computation patterns. There are small kernels, and overall, it's a very promising architecture because it got much larger capacity and is much more efficient for training and inference. On the other hand, the stability and elasticity side has a lot of even more issues to tackle, and because with even larger cluster with more nodes, we actually want to make the training more elastic, right? Because currently our single training job only handles fixed number nodes, but it would be really ideal if a single training job can have variable number nodes, right? And it makes the training much more flexible. And this is what we are currently working on. On the other hand, as I mentioned, our robust training framework can handle maybe 90% of the faults, but there are 10% that requires human intervention. And there are a type of errors that is very hard to debug or handle. There's the silent data corruption, where the hardware may have some bit flipping, some memory corruption, but there's no notification or exception from the CUDA side for the software to catch. So you may see at very low frequency that some of the training loss would suddenly go to not a number, and we have to pause the training and do some analysis. So that's something we're still working on. Okay, cool. So that's all about the stability side of the challenges. So now we have this MegaScale work. It has been running in production for a few months and scaled language model training for more than 10K GPUs, right? So we looked at the efficiency side of the challenges. We have built profiling tools. We help, which help analyze the performance and help us, innovate on the communication overlap techniques. On the stability side, we covered the robust training framework, which is very important because it helps us automatically handle a lot of GPU faults in a cluster and save a lot of human efforts. So this is a very good collaborative work with Peking University and a lot of colleagues at ByteDance, and I hope you enjoyed the talk. Thank you.